Okay, excellent. Thank you for that, for bearing with us. We have to fix the stage. But we have an exciting panel that will be led by Will Knight. I'm not going to introduce everybody. I think everybody will get a chance. But thank you, Will. You can take it away.
Thank you very much. Yeah, great to see everybody. Good morning. You've heard about vibe coding and the business of AI. Now we're going to go down the stack to what actually matters, I think, which is the hardware. I'm going to spare you long introductions of everybody. You can see everybody's up here. We had a late edition. And I think we should start by talking about how, so we're in this kind of amazing moment, right? Where generative AI has created this enormous boom, but also this huge demand for computer power and this huge, strain on the energy, and sort of we've got the environmental concerns as well. But that does create opportunities for new hardware and new directions. And I want to start by asking everybody how they expect the computing stack to maybe evolve. And I suspect everyone's going to have slightly biased answers based on their own interests, but I think that'd be very interesting. And we can start with Julie, who's very kindly brought a $1 million chip from Cerebras. So yeah, go ahead.
Hi, Will. Hi, everyone. Thanks so much for coming to the 9 a.m. session. Yeah, I'm Julie Choi. I lead marketing at Cerebras Systems. We are the inventors of wafer-scale engine. This is in my hand a third-generation wafer-scale engine chip, the largest chip ever made, the most powerful and fastest processor for AI inference and training. And I think that as we evolve, Will, we're just going to see even more innovative, novel approaches at the hardware architecture level, and looking forward to hearing from my fellow panelists.
And the innovation with this was that rather than cut the chip up, you just made a gigantic chip that can do new things, run more compute, so you can run an enormous model on it, right? That sort of thing.
Exactly. Yeah. This is all about measure, but only cut once. This is one perfect square cut from one TSMC nanometer 5 wafer.
Yeah, okay, and so Dinesh is not representing Grok, but is an advisor to several startups working in accelerated AI. How do you think things are going to evolve?
The compute space, as we look at it, is a combination of software and hardware. And on the stack, if I were to state it, is software running on hardware with a specific compute paradigm, with a computer architecture under that paradigm that uses a set of compute units. And the compute units can be your traditional CMOS, they can be optical, they can be quantum. But the stack that I've mentioned so far, that abstraction holds well for all sorts of compute, as I see it today and going forward. And after that comes, how do we actually manifest the various compute units into chips of the kind that Cerebras is showing, and whether that is at the level of improving the parameter network, bandwidth parameter, packaging parameters, and so on and so forth. The point is the optimization space is extremely large. The manifold on which we can look at potential solutions to the problems going forward is multivariate, and the space there is very large. So I encourage everyone to look at it ab initio. What we have done from the past, in the past, is in the past. Don't let the past constrain the future.
Right, very good. So Caleb, you're helping companies build AI, so you're sort of on the front lines of doing this. What do you think is going to happen?
Yeah, I think there's a lot of problems just on the entire stack itself. But I think as businesses start to look into integrating AI, there's a problem of ownership that's involved. So, getting a chip for $1,000 that can do all your entire workloads, or paying for cloud costs. So as the models themselves start to change, how can businesses themselves integrate them directly and get them for a fair price? Then also convert that AI and the energy involved into productive, utility.
Okay. That's very cool. Okay, we're going to continue going down the line, get more subatomic, I guess, or quantum. So Alexander, do you want to? Yeah. So tell us a bit about your company and how you envisage things evolving into some radically new hardware.
Yeah. So I think about hardware a lot because that is our bread and butter. We are thinking about. In a way, we had to take a step back and say, what is a computer and what could a computer be? And what we work on, I love that chip. It's such a great visual, and I wish I could have something like that. but we don't even have chips. We took the fundamental unit of matter of a single atom and turned it into the fundamental unit of information, which is a quantum bit. And the way that I think about hardware is, hardware in and of itself is a set of rules for constraints of what a computer can do. And with all of the amazing advances that we've had over the last however many years you want to pick, right? 52, however many, we are still limited by the same fundamental set of operations that we can do on a computer. We change the architecture, we change the connectivity, but it's still the same set of instructions.
Right.
And a quantum computer is the first time in human history where we can break out of that. And we can take advantage of the fundamental properties of nature to do something that is different and more powerful. And we are not today, necessarily competing with Cerebras or with any of these companies, but we are building really fast. And I want people to think about how exponential growth of technologies happens and how easy it is to underestimate, maybe overestimate in the short term what that progress will be like, but underestimate it in the long term.
Right.
And, I think that in a few years, we're going to be hearing a lot more about quantum computing and how it influences our businesses everywhere.
Okay, great. So Jeremy, this must be a wild time. You've been working in some supercomputers for a long time, and all of a sudden it's front page news, building vast amounts of compute. Do you see the nature of supercomputing changing, evolving, the hardware, the designs changing much?
So I'll let you know what we tell all of the folks here at MIT, all our scientists, about how they should think about computing. As a person who's been in the field, supercomputing for a long time, it hasn't changed at all in many decades. Every single computer at the high end that we built for the last many decades have only done one operation, which is variable precision matrix multiply. So there's a lot to unpack there, but it's for very deep mathematical and physics reasons. That's the only operation we've ever been able to figure out how to accelerate over many decades. And so what I often tell the users, the computer picks the application. AI happens to be acceleratable by that operation. If it was not, this meeting isn't happening today. We'd be talking about something else. And so what I always tell people is, think about whatever you want to do, and if you can accelerate it with that kind of mathematical operation, the sky's the limit on what you can do. And someone in your field will figure it out, and they will move ahead dramatically. That said, the quantum world is different, and we don't know how that's going to play out. And as was said before, it is fundamentally different, and it may break this paradigm, but that's where we are today.
Well, I'm very interested in this topic because I feel like there's a lot of opportunity for the design of supercomputers, a lot of activity. The big companies are thinking about it. There are a couple of MIT spin-outs that are doing optical interconnects. Do you think that's going to pay off? That's one thing
the optics advantage has been something that has been recognized for quite a while. The engineering challenges have been quite significant, but I'd say it's definitely becoming mainstream. We've had optical for long haul for a long time, and it's just a matter of how deep you take that into the chip. And I think you're seeing it get very, very, very deep nowadays. So I think it's expected that optical networks will go very deep into the computers.
Okay, great. So Jeff, returning to quantum, I'm sure people have probably heard of things like Google's, Willow chip and the advances that Microsoft has been making. I feel like I'm personally in this sort of superposition of being excited and then just thinking it's never going to happen. Are we really going to see a quantum, from a scientist perspective, research at the very frontier? Do you think that we're likely to see this take off in the next, I think Jensen was saying 10 years, but where do you think it would be?
Yeah, I think a lot of people, if you look at the stock response to Jensen's comments, they took it as a negative because all of the quantum stocks tanked. But when we talked about it in our research group, we're actually quite excited about this because his answer wasn't 50 years or 100 years. It was something kind of in the near future that is visible and tangible. And I kind of agree with his assessment that on that 15-year timescale is when we'll probably see systems large enough and powerful enough that they would have impact on real-world problems and doing things of like practical relevance that you wouldn't be able to do on even the largest supercomputer that you could come up with. And so, yeah, those are really the problems that we're envisioning tackling with quantum computers are like, even if I take a Summit supercomputer and make 100 of them or 1,000 of them, the answer is still untenable. And hopefully those are the things we can attack.
Okay. So I want to return to software because obviously there's an interplay. And Caleb, we were talking earlier about how you see the software world evolving. And I thought this is very interesting. I'm fascinated by the vibe coding thing I've been trying to build. I've been building some things with my 8-year-old, and they often work great, and then they just completely break. And so I was very interested in your thoughts. Can you share more on that?
Yeah. So I think that the actual programming languages that everyone at MIT at least is familiar with were built for people, you know.
Right.
And the actual way that you recall information from a library or you get documentation, the structure of that is built for people. So how do you actually change that to build languages and tools that AI can use, right? And AI can spend, 30 seconds going through a bunch of documentation, going and specifically picking out the important parts to supply to the user. How can you allow the model itself to compare that documentation with code? How can you incorporate things like type information, the actual compute architecture you're compiling that for, into the actual language so that the model can get all of that out? Right now it's built for people. There's tools like LSPs or language servers that are built into every single IDE or coding environment that any developer uses. And again, those are also built for people. How do you expose that to the language models themselves? And I mean, there's also the kind of fundamental aspect of code itself, which is text in nature. And it's probably one of the most densely encoded pieces of text that you can use for computing. And if these models are the ones that are going to be applying onto the code, what is the right kind of structure? And there's a lot of different tools that are out there. There's models that are using parsers built in directly to verify their output. I think this new wave of reasoning models themselves will also be very important for coding with AI.
Right, yeah, so it seems to me like a message for people, maybe startups or working at companies, is that you need your developers to be really experimenting and aware of how quickly things are moving. So Dinesh, Julie, let's talk about companies experimenting with hardware. So how much are you seeing, Julie, you can start with you, how much are you seeing sort of adoption of exotic new chips and so on?
Yeah, it's been a really exciting time at Cerebras. We launched Inference last fall, right? Will, I think I saw you, we see you every year at NeurIPS, and we catch up. But Inference, especially with the fact that Cerebras is serving the fastest open source llamas, DeepSeeks in the world. So just last week we announced almost 2,900 tokens per second. 2,900 tokens per second for Llama 4, which is basically the fastest in the world. And we continue to serve these very large open source models that are extremely rich for developers through Cerebras. And so what that's doing is building a bridge between the bravest developers. I would say the early adopters tend to be very courageous, and they're willing to code on things that they've never seen before. In fact, they want to go at Ferrari level speeds. People call this, the developer community dubs this, the caviar of inference. I personally like to drive a little slower, but Naveen Rao, my friend, he liked to drive Ferrari. So I think there's something about the speed of hardware and the speed of AI development that we're kind of seeing a synergistic thing right now.
Right. Well, speaking of Ferraris, Dinesh, you are famous for, you're not here representing Grok, but Grok was very famous for making this big splash with super fast inference and showing what you could do there. So how important is that for companies, this sort of gaining an edge in speed of inference?
Before I answer that question, let me start with, you asked exotic chips.
Yeah, I'm sorry, please.
Actually laid out the framework for the exotic, the various dimensions of exoticness, so to speak. So it's exotic at the chip level. That's one aspect. And exotic at how we package, put things together. Cerberus has done a great job there. And then there is exoticness at the architecture level. There is exoticness at the paradigm level. And then we have at the compute unit levels. You have the optical compute, the optical communications, quantum compute, and these are all at the compute unit level. As it comes down to most things, when you optimize, when you enable the larger space, and the space is larger when you get to the compute paradigm, the variables dimension space there opens up significantly. You can optimize for performance, power, and cost. You get all of them all at the same time.
Right.
So what Grok, I'm not representing Grok, but what Grok has done is enabler and of all of that. That's performance, that is cost effective, that is power effective, and that can scale. It's a Ferrari that you don't need to park in your garage and drive on the half an hour on the weekends to show that it can run 300 miles an hour. It's a Ferrari you can run every day for your commute.
Right.
And by the way, you don't need stop signs because you can synchronize.
So you got to get your groceries in the Ferrari.
So that's what the exoticness, quote unquote, as you open up the space, it allows for that optimization. And that is where I see the possibilities, more and more possibilities going forward. That is what we should be looking at, enabling, not trade-offs, but enabling, being able to serve all the requirements as an and. A Ferrari, that is a day-to-day commuter.
Right. We'll move on from the Ferrari metaphor. But for end users, customers, companies, what are the pitfalls, do you think, in trying to sort of chase this optimization? Can you end up...
local optimization.
Well...
A Ferrari that is not even street legal.
So you've got a very fast system that doesn't run everything you need to have.
So it's great to show off, but it's not street legal.
Right. Yeah. Okay. Well, so let's go over to the quantum world. Actually, let's start talking a little bit about Moore's law, the end of Moore's law, which has been something we've all heard about forever, and it seems like it's never really come to pass. But Jeremy, maybe you can start by telling us what your perspective is on that. Are we really? I mean, I think we are really bumping up against the edges in that. How does that manifest?
Yeah, and I would say that what has surprised us is the general utility of this operation I talked about to move business forward, and the extraordinary level of investment that has attracted to create new technologies, which is well beyond what we ever thought. I mean, Moore's law was underpinned at some level by a belief that there was an upper limit on the amount of money that could be spent. And I would say right now, Moore's law, within the confines I described before, is probably pretty strong for another decade. The innovations you see happening with respect to, you think about what's going on with the Blackwell chip and, these 4-bit operations that are happening that seem to be good for large language models. There'll be something you hear a lot about in the future called the Ozaki scheme, which will completely simplify that and make these chips a lot more manufacturable and a lot simpler. And so I think we got a good decade in that very narrow space that I described. I would say, the traditional single core general purpose space has been pretty well pegged for a long time. And so, we don't see much there, but in this narrow space, it's pretty strong for another decade.
Well, so I want to ask, because we're at this incredible moment where there's this talk of, building unprecedented, sort of unthinkable amounts of compute, and also bringing a lot of compute back to the US. What do you think, as an expert on building these, hyperscale systems, what is the biggest challenge in building that enormous amount of compute here?
I would say that, obviously onshoring the leading edge fabs, as people are, thinking about that, there's clearly things going along there. as one saw in the recent news, just taking the chip and then integrating into the packaging, a lot of that, I mean, I think, I saw somewhere a chip like travels 60,000 miles before it gets to the user. So there's a lot of globalization in that as well. So I would say, people think about the chip, but I think it's the stuff between the chip and then getting it into a server that just goes all over the world. And, how much of that you want to bring here is a big supply chain industrial challenge that those are all choices people have to make, how much of they want to bring to the United States or to certain particular regions. And so I would say there's a big supply chain challenge that it has to be figured out.
Okay, so Alexander, thinking about 10 years or more, Moore's law, maybe that will have a big impact on quantum and other approaches. When it comes to your company and just quantum in general, what do you think that the first use cases are likely to be? What will people use quantum computers for most immediately?
Yeah, I have 3 answers to that, so I'll try to be brief.
Okay.
I think that the first area where we're going to see quantum computing's impact is going to be in research. And I could say that this has been the history of computing overall. Research has always been advanced by having more computational power, and there is a downstream effect of that in the products that we build and the businesses that we can create. I think that for the vast majority of the audience, that's not what we're looking for. We're looking for where is it going to come in business. And I think that there are right now already early indications of usefulness or future usefulness in problems that are very varied in optimization, in simplifying the resources that are needed for classification problems and machine learning. But I think that the earliest use cases that we are going to see for wider spread adoption for quantum computing actually integrated into supercomputing systems is going to be for pharma, for materials, for chemistry. These problems at their core, and going back to this idea of there's one thing that we do today that we do very well. These problems at their core are trying to answer what happens when atoms and electrons interact with one another and develop these emergent behavior, right? Like how we think about chemistry, how we think about drug interactions, how we think about material properties, all comes from electrons and atoms moving around, bumping into each other. And the thing that we just cannot avoid is that we end up having to describe these things mathematically as a problem that is described by quantum mechanics. And the underlying architecture of a quantum computer is much more well suited to answer these problems than a classical computer.
Right, so when it comes down to it, everything is affected by these quantum effects, and so you just exploit that. I mean, there was a time not so long ago when every finance company seemed to have a quantum computing officer, right, or quantum expert. Jeff, the same question to you. What do you expect? Do you think like finance or maybe even in AI? Because this is, there's people are desperate to find an edge, right?
Yeah. So I should preface this with I'm not an algorithms expert. I work on hardware, but my feeling is that these future quantum computers, their actual clock speed, if you were to kind of compare it to even the thing running in your M4 Mac, are quite slow. And so you probably won't want to use it for like real-time high-speed trading applications. Like that's not going to be the use case of these computers because their effective clock rate is slow. And where they really win is with scaling, where the kind of complexity and size of the problem becomes so large that even with a slower clock, I still beat a very large classical computer. And so my sense is that for high-speed trading in these things, there's probably not so many use cases. Maybe doing, offline portfolio optimization could be a potential use case. For AI, it's also a little less clear. I think the field goes back and forth with whether or not quantum computing would be useful for things involving classical data. So classifying images and, whether it's a cat or a dog, these kinds of things, there's an inherent data loading problem where I need to take classical data, shove it into a quantum computer, which incurs overhead. And then if the underlying quantum algorithm can't overcome that overhead with its speed up, then it's basically a wash. And I think right now there's not clear evidence that it will help. But for problems of quantum data, so the things that, again, are probably interesting for research applications and maybe things related to pharma, maybe there's some AI application where the data is inherently quantum and it already lives in the quantum computer, and I don't have to do this this data shoving into the system.
Okay, great. Well, unfortunately, we're out of time. I wish I could give you all a bit more time, but thank you all for joining me. Please join me in giving them a round of applause.
Thank you.
Thanks.
Thank you.